who aren't able to make it. All right, so we're starting with Unit 2 Progress Check, MCQ Part B, number 8. The question is, a block slides with constant velocity down a rough inclined plane that makes an angle of theta with the horizontal. It experiences 3 forces: gravitational, or F sub g, normal, F sub n, and frictional, F sub f. Which of the following gives the magnitude of the net force on the block? Okay, so since it's moving with a constant velocity, that means it is not accelerating. So since it's not accelerating, it is moving downwards and to the side, but with a constant velocity. So I think because there's no net acceleration, because it says that there's a constant velocity, my default would be to go that there is no net force. And I'm not sure if I'm right. I am. That's good. As the teacher, I should be right. Well, not all the time. I can make mistakes, but it's nice. So basically, that one's a really complex question, right? It appears to be a complex question because the first thing I would think about was like, okay, I got force of gravity and then the normal force, and then I know that the net force would be like this, in between those two, and then the force of friction pushes backwards. But it gives me a hint, the constant velocity. So that term constant velocity indicates that it's not speeding up and it's not slowing down. And since there's a constant velocity, there is no net acceleration. And since force is equal to mass times acceleration, there is no net force. Does that make sense on that one? That was Alex's question. So Alex, let me know if that.
Yeah, that makes sense.
Awesome. Perfect.
Thank you.
Yeah. Holden, did you have 1 or 2 from a different test? Or 3 or 4?
I have some from this MCQ number 1.
Perfect. And that is on the practice test?
Yeah.
Okay.
So number 9.
Okay. Yeah. You want to give me the whole set?
Sure.
Or we'll start from number 9 and then we'll figure it out from there. Yeah?
Yeah.
Okay. So question number 9. 2 skaters are initially at rest next to each other on frictionless ice. Skater A pushes on skater B. If skater A has a greater mass than skater B, which correctly relates the magnitudes of their momentums, P, and their kinetic energies, K, after the push? Okay. So the first off is, since they are initially at rest and they're motionless and the ice is frictionless, if I push on one, it should push back on the other one. So for momentum, are they going to worry about negativity? I think. So the step number 1 is figuring out whether they're saying that one is negative and one is positive. Now, did they use the term magnitude? They do. Okay, so they say it correctly relates the magnitudes. So I don't have to worry about negative and positive. I don't have to worry which direction they're going. I was worried initially that if we didn't define positive, then the positive one's bigger than the negative one. But since it's just magnitude, direction doesn't matter. So the first thing is, I would say momentum has to be conserved, because momentum is always conserved. So if one person pushes against each other, even if their masses are different, the heavier one will go slightly slower, the lighter one will go a little bit faster, but mass times velocity has to equal mass times velocity. So the momentum has to be equal to the momentum. So that gets me down to A, B, or C, because the momentums are the same. Then the kinetic energy, I have an option with A less than, A equal to, or A greater than B. So Since the heavier person, the greater mass person, is going to be moving slower, I know that velocity is going to end up getting squared. So that slower person, that squared value of velocity, the velocity matters more. So the lighter person is going to have greater kinetic energy because the velocity gets squared, the velocity matters more, and the lighter person has greater velocity. So skater A had greater mass. It doesn't actually matter who's pushing and who's being pushed because the force is equal on both of them. But skater A has greater mass, so skater B should have greater kinetic energy. So KB should be greater than KA. I believe the answer should be A. Let's see. Yay! It is. Did that make sense without putting numbers to it? Okay. So yeah. Okay. So basically I have to make sure that the momentums match because momentum's always conserved. Kinetic energy doesn't have to be conserved. So then the velocity being greater for B plays more of a role. Okay, do you have another one from this one?
Yeah, I was going to say number 5 with the springs.
Ah, yes. Okay. So this is a tricky one. So the way that I would start with this one is it's a block of 3 kilograms hung from a string, causing it to stretch 12 centimeters at equilibrium. The 3 kilogram block is then replaced by a 4 kilogram block, and the new block is released from the position shown above at which the string is unstretched. How far will the 4 kilogram block fall before its direction is reversed? Okay, so 12 centimeters would be at its smallest. It can't go any, or sorry, unstretched right here would be at its absolute smallest. 12 centimeters is with a 3 kilogram mass, which creates a force of, let's say, 30 newtons, multiplying by 10 meters per second squared. 4 kilograms, because I know that the spring is a consistent spring, and F equals KD, the spring constant is the same on the spring. So if I increase the force from 3 to 4, I would increase the distance that it stretches by the same ratio. So if 3 kilograms stretches 12 centimeters, using the same ratio, 4 kilograms would stretch 16 centimeters. Because 3 times 4 is 12, 4 times 4 is 16. That's using the equation F equals KD, or F equals K times X, I think is listed on the AP equation sheet. And since I'm increasing the force by 4/3, I need to increase the distance by 4/3 because the spring constant remains the same. Now that gets me to 16 centimeters, but 16 is not an option here. So 16 centimeters would be to equilibrium. But if I'm on a spring, it's going to go 16 centimeters from 0 to equilibrium, but now I'm moving fast. So I would go another 16 centimeters down to my lowest possible point. If I'm 16 centimeters up from equilibrium, I could also be 16 centimeters down from equilibrium. 16 and 16 is a total of 32. So my answer would be 32 centimeters. Indeed, it would be. So that one starts with the idea that a spring constant is constant. F equals KD. I haven't changed my spring constant. I have changed my force from 3 to 4, so I have to change my distance from 3 times to 4 times. If 3 times is 12, 4 times is 16, and then double it because it's distance to equilibrium and then equilibrium to the low point. That one track? All right. Any others from this one? Okay. Holden saying no. In that case, let's switch gears and let's do some practice problems. Okay, so for these ones, I am going to run through a set of practice problems. These were created by another AP Physics teacher, and it's a heck of a set. So, and it's split by units, which is really nice. So if I can find the accurate zoom, come on, baby. Sorry, trying to get the iPad to Zoom connect correctly. Not liking that. Cancel, stop share. We'll try again. Thanks for bearing with me. Please, 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 please work. This will make so much more sense if we can see me writing. I apologize, guys. I tested this technology at school, and then I switched Wi-Fi networks when I came home. And now, obviously, it's just not loading. So ain't that a thing? Let me double check, see which network we're on. Settings. Wi-Fi not connected. Let's connect to the Wi-Fi then. There we are. Okay. Try that again. No, don't want to screen share to Roku. Sorry, guys, this will be my last try. And then we will, hey. I just had to put it into the universe that I was about to give up. The universe loves quitters. Unlike TJ Lavin on the challenge. Okay, so here we go. So we're gonna run through a bunch of different questions. These were created by Michael Friedman, credit where credit is due. So these are unit by unit, and I really like these because they allow us to kind of talk about what we're seeing in various pieces and talk a little bit about thought process. So starting at the beginning, a light sphere, a ball, is thrown upwards on a cliff at t equals 0 seconds and experiences a significant drag force. So the air is going to push on it. The velocity time graph is shown above. So the first thing is paying attention to what types of graphs we're looking at. Velocity time, and it's measured, velocity time. And that's nice because personally, I process most things as velocity versus time more easily. So as we get to non-velocity time, I might even convert it to a velocity versus time graph. Which of the following describes the direction of the sphere's acceleration just after the throw and the time that the acceleration first reaches 0? Okay, so I need to remember that acceleration is equal to the slope of the velocity graph, because acceleration is the change of velocity. So now I'm just looking at slopes. Just after the throw would be like right there. So the slope is really big and negative. And then when it first hits 0 would be like there-ish, right? When it gets flat is where the slope is flat. So the velocity is originally, the acceleration is originally negative, which is going to be down, one of these two. And then when does it hit 0? or it would be at 1.2 seconds. So that would give me D. Questions on any of that one? Great. Big idea is that the acceleration is the slope of velocity. Okay. Question number 2. For problem number 2, we again have a velocity versus time graph. Things just keep coming up, Mr. Williams. A student pushes a cart horizontally in the positive direction on a frictionless horizontal table, and the graph of the motion is shown above. At which of the following times does the student apply the greatest force to the cart? So a student's pushing it, applying the greatest force. Now, this is a velocity versus time graph. I would start with the idea that force is equal to mass times acceleration. So force is proportional to acceleration. I just established that acceleration is the slope of the velocity graph. So I'm looking for the time that the slope is the biggest. Right here, the slope's like 0. It gets the biggest when it gets the steepest, right about there. Dot, 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 dot. That would be about 0.8 seconds for answer B. Anybody process this one differently? Different order of thinking to suggest? Cool. Big idea. Force creates acceleration. We're asking for the greatest force. So I got to think about when it's speeding up the most, not when it is the fastest, right? Because it takes 0 force to just keep something going at the same speed, assuming no friction. Great. Let's then move to number 3. Okay, so question number 3, I now see I've got an acceleration versus time graph. So this is not my favorite type of graph. It's not a velocity graph, but I can deal with it. So this one's giving me the slope. Now, the reason that I say I like velocity is because velocity, it's really easy to see the slope, and it's really easy to see the area under the graph, and that means I can go to acceleration or I can go to distance or position. The acceleration versus time graph of an object moving in a straight line is shown above. The object starts at the origin with an initial velocity v sub 0. Which of the following can be concluded from this graph? Oh, okay, so this is like a double not my favorite type of question, because it also gives me 4 things and I have to test all of them, right? Because it gives me 4 options and it's like which of these could be a correct thing. I kind of have to go through and see whether it's possible or not. So the first one would be the object is in free fall. So free fall would be falling due to gravity. What's the acceleration due to gravity?
9.81 meters per second squared.
Perfect. And it would either be negative or positive. I'd assume it would be negative. So if that were true, my line should be like there, and it is not. Even if I was on a different planet, acceleration should remain constant. So even if I wasn't on the Earth, or if I said, I made it the opposite way and said it's positive 9.8, it's still a flat line. So neither of those is correct. A is out. B, the object is furthest from the origin at time equals 2 seconds. So 2 seconds would be right there. Now that's looking at the distance. So since it starts at v sub 0, right, my original velocity is v sub 0, and I'm starting with a positive acceleration, that means I'm speeding up, and I'm speeding up the entire time up until 2 seconds. Then, as I go negative, am I moving backwards? What does a negative acceleration mean?
You're just slowing down.
I'm slowing down. Can I still be going forwards while slowing down? For sure. So since I was speeding up this whole time, I've probably gone quite a ways. Now here, I'm starting to slow down, but I'm still going forwards because I started at v sub 0 and then I increased my velocity all this time, right? If I was drawing this velocity graph, velocity time, and I start at say v sub 0, I would start with a really intense acceleration, right? It'd be really steep. And then I'd slow down right there, right? That would be at like 2 seconds. But then I'm still going with a positive velocity, right? I'm still going with a positive velocity through here. So I'm not at my furthest from the origin. So I would argue that is not a great answer. It's not at the furthest. The object has a velocity of v sub 0 at t equals 4 seconds. So at t equals 4 seconds would be here. Well, at that time, the velocity is the area under the acceleration curve. So that'd be that and that. So these two triangles would end up canceling each other out, putting me back at an original velocity of v sub 0. That one sounds valid, right? At v sub 0, because by 4 seconds, I would, in fact, get to that point. Because my acceleration for the first 2 seconds has been canceled out by my negative acceleration for the last 2 seconds. And so that would put me back at the same original velocity. Or on my velocity graph, there's 2 seconds, there's 4 seconds, I'm back to that point. And then my last option, the object experiences a constant net force. That one can't be true because force equals mass times acceleration. If I had a constant net force, I would have a constant acceleration, which I don't. So I would go with C on that one. Cool. All right, problem 4. No graph, just words, no diagram even. Okay, a block slides without friction at speed v off a horizontal table. V, and lands on the floor. Which of the following pairs of measurements would allow one to estimate v? Choose 2 correct answers. Okay, so to estimate the original starting velocity, I need to know, well, I know that it's going to fall at acceleration due to gravity. So first, I need to figure out the vertical distance, right, delta y. Then I got to figure out something horizontally, horizontal distance or time. So I need a horizontal component and a vertical component. Because at first I got to figure out the vertical to figure out time in the air, right? So number 1, solve for time in air. Number 2, I can figure out the vertical or the horizontal part. So the horizontal distance from the table and the time in the air. That would work, right? So A would be viable. I have a vertical and a horizontal component. The time in the air and the height of the table. Those are both controlled vertically. So that one's a no-go because those both control vertically. Horizontal distance from the table and the height of the table. Horizontal distance, delta x, is horizontal. Vertical distance is vertical. C is looking good to me. Vertical velocity just before reaching the ground and the time in the air. Again, those are both vertical. Those tell me the same thing. So because I need a horizontal part and a vertical part, I would go A and C. Question? Okey-doke. Number 5. Which of the following position time graphs is consistent with a cart moving in a straight line with a net force in the opposite direction of its direction of motion? Okay, so a force in the opposite direction means I have a negative acceleration, right? An acceleration slowing the thing down. So I would think about this if I had no acceleration, right? And I was just moving in a straight line, I would just go straight up. This is position versus time, right? X versus t. So if there was no acceleration, it would be straight up. If I was slowing down, I would get less and less fast, so it would look more like that. Right, I'm slowing down instead, so I'm reducing my slope. That puts me at A. The other option is I could have gone negative. So I could have said this is also a valid option, or this is X and this is T. It's still moving in a straight line. And then as it's slowing down, the slowing down would mean I have to get less negative, so it would go more like that. And that is not the same as D, right? Because this one, it actually gets steeper because that is getting steeper there. That's no good. I need it to get less steep. So that's A. Interrupt me as this is not making sense. Okay. Cart of mass M is moving uphill at speed V. A rope pulls on it parallel to the incline with a force of magnitude T. What is the magnitude of the net force on the cart? Okay. So the cart is moving uphill that way. A rope is pulling down with T. So let's start by doing all the forces. The fact that the cart's moving up, if it's going at a constant velocity, the initial velocity doesn't really matter. There is, however, another force acting on it. What's the other force that acts on the cart?
Gravity.
Good. So I have a force down due to gravity. Then I do have that force of tension, right? Now, we could argue that there's also a normal force there that keeps it up off the ground. But gravity and normal are going to kind of cancel parts of each other out. So what I'm going to be left with is the tension and then just the downhill component of gravity. I'm not worried about the into or out of the ramp because the out of the ramp part is going to get canceled out. So if I zoom in on this part of gravity is going to get canceled out by the normal force, right? So this is F sub G in the y direction, and that's equal to the normal force. So those cancel each other out. What that leaves me with is just that part right there, the downhill part, which I would call like F sub G in the x direction. So then I got to figure out what that is equal to. Well, I've got that angle right there. That angle is going to be equal to theta. So this becomes theta. I know that down the total of gravity is going to be mass times acceleration due to gravity, because F sub G equals mg. Now I will care about that part. That is the opposite of this. All right, my opposite of that. So sine of theta is equal to opposite over hypotenuse. Sine of theta equals F sub gx over mg. So to solve for F sub gx, that would be mg sine of theta equals F sub gx. And then to find the total force, it would be F sub gx plus F sub t, the force of tension, which they're calling regular t. They're not calling F sub t, they're just calling it t. So I'm left with mg sine theta plus t. And that is an option. It's option D. Now, let's say you were also in a position where you looked at this and you were like, oh, I don't know how to calculate that. Is it a sine? Is it a cosine? Crap, I can't remember. Totally valid. The next thing that I would think about is, well, I know that it's equal to the tension plus some part of gravity, right? So it's the tension plus some component of gravity. And then if I look at these, well, this is tension minus something. Gravity is not pushing it up the hill. Gravity is pushing it down the hill. So that one's out. This one has a minus, tension minus something. And then tension plus mg parentheses sine theta. Well, sine, like the angle, doesn't play on tension. Tension is along the ramp. So by process of elimination, you could probably get there too by knowing it's tension plus some part of gravity. So you probably don't have to do all this like normal force, cancel out the vertical, as long as you can remember the downhill part has to be the part that we care about. Any questions there? All right, let's keep playing. Problem 7. A cart moving at a constant speed, v, moves towards an ideal linear spring attached to a wall. The cart bounces off the spring and returns to the left again, moving at speed v. Which of the following describes the acceleration of the cart? Choose 2 correct answers. Okay, so I'm paying attention to the acceleration. And it's going at a constant speed v. So part A is the cart's acceleration is 0 while not in contact with the spring. Yes. Constant speed means no acceleration. So A is a good answer. Right? When it's not touching the spring, it's going at a constant speed. That means no change of speed or no acceleration. B, the cart's acceleration is constant while in contact with the spring. So when it's hitting the spring, the acceleration is proportional to force. Is the spring pushing the same amount if I'm just barely touching it or if I've pushed it all the way back? It is not pushing the same. The further I push the spring back, the more it wants to push me back, right? The more the spring compresses, the more it pushes back. So B is not a great answer. The cart's acceleration changes direction when the cart changes direction. I do not think that is true. I think as soon as it hits the spring, its acceleration is going to be in that direction. And the entire time it's touching the spring, the acceleration is still going to be in that direction. It's going to be slowing down at first, and then it's going to be speeding back up. But when it's slowing down, acceleration is that way. And when it's speeding back up, acceleration is still that way. So I don't like C. The magnitude of the cart's acceleration is greatest when the cart is momentarily at rest. Bingo. That gets the same idea as B. Acceleration is proportional to force. It's pushing the most when it's fully compressed. That's when it's at rest. And then I'm pushing it back from there. So that would be the greatest force and the greatest acceleration. I like A and D. Cool. All right, number 8. An asteroid moves toward planet P on the trajectory shown, only under the influence of planet P's force of gravity. Which of the following describes the speed and the acceleration of the asteroid at this moment? Okay, so I could remember that the force of gravity is equal to big G mass 1 mass 2 over distance squared, or the radius squared maybe, r squared. But I'm not sure if that's super helpful. It does tell me that acceleration is going to increase as I get closer, but I also kind of know that. All right, so the speed as I get closer to the planet, I'm going to speed up. Drop something, it speeds up as it gets closer to the planet. So the speed has to be increasing. I'm to A or B. The magnitude of the acceleration. Since I'm getting closer to the planet, I'm now getting a greater force. The closer I get, the more d gets smaller, the more the force increases. So my acceleration should also be increasing. We could also think about this one as a potential to kinetic energy problem. So I could say for the speed, I am going from high potential energy. And as I get closer, so I'm doing PE here, where I have greater potential energy. As I get closer, my PE goes down, so it has to transfer to my KE going up. So I would go with A, speed is increasing, acceleration is increasing. Questions, comments, thoughts? Oh, I got something in the chat. This is awesome. Oh, I'm sorry, I need to go. Okay, no problem. I will keep recording for you. At least somebody said something. I like something. Thank you. Have a great day as well. All right, 9. 2 planets, both of mass m, are a distance d apart from each other and exert a force F on each other. If planet 2 is replaced by a mass 2m, so if in this planet 2 becomes 2m instead of 1m, but the same size and located at the same distance away, what will the new force on each planet be? So the first thing to remember is that every force has an equal and opposite force. The force of planet 1 on 2 is equal to the force of planet 2 on 1. So both planets should have the same force on each other. So the force on planet 1 from 2 should be the same as 2 from 1. So B is out because they're different, and C is out because they're different, right? And I can't have the force of 2 objects on each other be different from each other. Then the next piece is I've just increased my mass from m to 2m. So I had that equation, F equals big G, m1, m2, over the distance between them squared. I haven't changed the distance between them. I haven't changed big G. I haven't changed mass 1. What I have done is I've doubled mass 2. So that would mean I also have to double the force. If I increase the mass by 2 times, the force would also have to increase by 2 times. So I should end up with 2F and 2F, which is part D. All right. Problem 10. Doing well here, guys. 3 clay balls labeled A, B, and C are launched from the same height at the same speed. A is launched at 30 degrees above horizontal, B is launched horizontally, C is launched 30 degrees below horizontal. They all hit the wall before reaching the ground in times TA, TB, and TC, respectively. Okay, so we're looking at the time that it's hitting. Rank these times from least to greatest. Okay, so if I was looking at distances, then the one that's going up would be in the air for longer, and it would go further. The one that's going straight would go medium, and the one that's going down would go the least far. But I'm not looking at distances, I'm looking at times. And because I'm looking at times, I'm just going to look at what percentage or what ratio of the velocity is going horizontally. Because what controls when it hits the wall? It's the horizontal component, right? The vertical component is going to be the same for all of them. They're all going to fall with the acceleration due to gravity. So then the question is, how much of their original velocity goes horizontally? B is all horizontal. So because it's all horizontal, it should be going the fastest horizontally and thus hit the wall first. So time B is going to be the least. A and C both have 30-degree angles. So each of them is in at a 30-degree angle. So they both have the same amount of horizontal velocity. Since each one has the same horizontal velocity, they should both have the same time before they hit the wall, because their horizontal component is what's controlling that. So time A and time C would be the same, but it would take longer for them to hit the wall because A same height, okay, yeah, at the same speed. That's the big key point that they are launched at the same initial velocity. So I am looking at what percentage of it is vertical. So B should be the least. B is less than A and C, boom, C. All right. Next one. I'm actually gonna pause for just a second. I'm gonna take a look at everybody's faces and just do a little check-in, because obviously this is a very weird formatting, doing this through Zoom. So I just wanna check in and see, is this working and feeling productive? Would it be more productive if I showed the question, had you work on it for a minute, and then talked it through? How can I modify things to make this more thought for you and more good practice for you?
Yeah, I think give us a minute or two just to think through it first.
Cool. Let's do that. Okay. Do you want to try to, no, if I break out room, then you're going to lose this screen. So I'm going to keep everybody in the same room. Okay, so problem 11 then is a small ball slides down a frictionless surface after being released from rest at the top. Compare the speed and acceleration of the ball at points 1 and 2. So at the beginning, it's released from at rest. So velocity 0 is 0. You're looking at the greatest speed and the greater acceleration. Think through this one. All right, somebody who's feeling brave, give me an answer and a justification.
Answer C.
Great, why is the answer C?
Because there it has had more time to accelerate, but then it stops accelerating as the same rate as point 1. This is at point 2 that I'm talking about.
Yep. Good, so at point 2, it's further down the ramp, so it's had longer to keep accelerating for. You could also think of this as potential to kinetic energy. It's dropped further, it's had a greater change of height, so I should be going faster. So it's definitely faster at point 2. Acceleration is greater at point 1 because it's steeper. And the acceleration is due to gravity. And so the steeper it is, the greater that vertical component, I guess the horizontal, steeper goes faster. I don't know how to justify that on a physics side. Steeper things, it'll speed up faster. That's greater acceleration. Cool, good job, Alex. All right. Next one, problem 12. Oh, an Atwood machine. All right, hold your disdain in. Two blocks of mass M1 and M2 are connected with a light string around a frictionless pulley as shown. The force of static friction between the block on the table and the table is great enough such that the blocks do not move. Okay, so they're both stationary. Velocity is 0, velocity is 0, not going anywhere. What is the magnitude of the force of friction? So we're looking for the force of friction. Work on it for a minute. See if you can figure it out. All right, who can give me an answer and a reason? Or a reason and then an answer?
I got B.
Okay, why'd you get B?
So I looked at the physics sheet and it says that the force of friction is equal to the friction coefficient and the normal force. So B has the coefficient for friction, and then the normal force is just going to be the two masses times the acceleration due to gravity.
Cool. All right. Anybody agree or disagree? Nobody agrees or disagrees. All right. So Alex, I think your thought process is perfect there, right? You found an equation that worked really cleanly, and you would be right if mass 2 was also pushing down on the table. So if mass 2 was up here, where its force was being pushed down, that would be the correct answer. However, in this particular case, mass 2 is not touching the tabletop. So the way that I would think about this one is that the force of friction is balanced on mass 1 by the force of tension. Since it's not moving, force of friction equals force of tension. And the force of tension is equal to the force of tension on this part of the rope, right? The force of tension on the whole rope is the same. And on this part of the rope, it's really F sub g of mass 2, which would be mass 2 times g. So I would go with D because M2 is not pushing down. M2 is actually pulling sideways. And that's what would balance out my force of friction, since it's not sliding. If it's sliding, it gets more complex, and then I have to use that static friction coefficient. Since it's not sliding, it's just sitting still. I haven't reached that static coefficient friction or that value yet, so I'd leave it there. That's a tricky one. All right. Another tricky one. Same setup. Two blocks of mass M1 and M2 are connected with a light string around a massless, frictionless pulley as shown. The surface between the table and the block is frictionless, and the block on the table is given a tap to the left. After the tap, while the block on the table is still moving left, so now there's no coefficient of friction, it's frictionless. While the block is still moving to the left, right, so I'm going this way, how does the tension in the string compare to the weight of the hanging block, M2G? So my question is, I've got force of tension here. The weight down here would be F sub G. What's the ratio between those? Which one would be bigger or smaller? That's equal to M2G. See what you can do with that. All right. Who's got an answer on this one? This one is admittedly, I think, is really tricky. I can see good justifications for two possible answers. Anybody feeling bold?
I'll go with C.
Okay. And why do you think the answer could be C?
Because it has to defeat the inertia of mass 2 as well as the force of gravity acting upon mass 2.
Okay. So you think the tension up is going to be greater than the gravity down?
Mm-hmm.
Okay.
And
Anybody?
because it results in upward movement. So gravity can't be winning,
Results in upward movement.
right? Yeah, if mass 1 is moving left,
Oh.
then mass 2 has to go up.
Yeah, okay, so step one is I drew my arrow the wrong way. I misrepresented this, right? Left means that way. So you're right, it's going up. Ah, look at that.
Yeah, so then the force of tension must be greater than the force of gravity.
Okay. Other arguments one way or the other? Okay. I gotta be honest, I've kind of confused myself on this one. So I think, because I had it sketched the other way, I had it sketched going to the right instead of to the left. I misread, well, I read the question correctly, but I drew it incorrectly. So Alex is making the case that it's going that way. Gravity is pulling down, but because the mass is going that way, so there still has to be an overall force downwards, right? Even if I'm pushing that way, I still need an overall force down because F sub T, F sub G, there is no force of friction. F sub F equals 0. But the tension force would be equal to M1 plus M2, because it has to pull both of them, right? Times G. I've got myself all tied in knots now. So somebody's got an argument. Alex says C makes sense to me. So the hanging mass is moving upwards, but acceleration still has to be downwards because there's the weight of the hanging mass. For the system of just the hanging mass, there's a net downwards force. So I've got the answer as A. However, my justification for it is not strong. I have a gut feeling that it still has to be accelerating downwards, because M2 is pulling downwards. M1 really isn't pulling at all. Like there is no force of friction. And because there's no force of friction, there's nothing that's pulling it in that way. I've got nothing pulling there, no force. I have a velocity that way, but the velocity itself isn't applying a force. It's a pre-existing thing. And so my force of gravity down I apologize. I need to do some thinking on this one in terms of why it feels right to me. A feels right to me. Checking the key, A is listed as the correct answer. And my gut feeling is that there has to be an acceleration downwards, that the mass 2 will end up pulling downwards and speeding up as it pulls downwards. But I apologize, I don't have a really good justification for why in terms of my thought process. Can anybody think through a justification on why the tension has to be less than the mass times the gravity, other than my arbitrary feeling that it should be accelerating downwards? All right, solid job working myself into a pretzel then. I'm gonna see if I can't get a better understanding on this one, and then I will come back to you and give you a better answer. Temporarily though, let's shift to problem 14. Problem 14, a student stands on a, see, embarrassingly, I actually prepared for all these questions too. I just had it drawn the other way. And since I had it drawn the other way, it made a lot more sense in my head. And now I've drawn it the right way because you noted that it goes to the left instead of the right. And now I'm confused. A student stands on a stale holding a box. At a certain moment, they suddenly lift the box over their head, then hold it there. Which of the following graphs best represents the reading of the scale over time? Think it through. So holding a box, pushing the box up, and then holding it there. Okay, so I gotta be honest, I have to solve this one by physically doing it. So if it helps you, stand up, pretend that you're holding a box, lift it, and see how the pressure feels on your feet. It's a slight change, but you can kind of get the feel. In terms of push on your feet, which answer feels more correct, or which answer is more correct?
I said C because, like, as you lift it, it's gonna, like, the forces are opposite, so it's gonna push you down a little bit, and then when you get to the top, like, the momentum of the box want to keep going, so it'll, like, lift you up a little bit.
Good. That is how I process it as well. I think the correct answer is C. As you're pushing the box up, you're applying a force up, so the box is applying a force down on you, and you'll see your weight increase. I actually did it on a scale because I just had to like double check it. And I saw my weight go up by about 20 pounds. I did it with like big weights just so I could see a significant difference. I saw my weight go up by about 20 pounds, and then I got it up there, and my arms kept pulling me a little bit, and I kind of lifted up just a tiny bit. Basically, you're making a jumping motion, right? And as you jump, you push down real fast at first, so that increases your weight, and then you lift up a little bit, and that decreases your weight, and then you go back to normal. So C is an accurate reading. You're providing a push, so that's pushing you down, and then the momentum carries you upwards a little bit, and that decreases your weight. Nice. 15. Astronaut is stuck at rest relative to a spacecraft 15 meters away. Which of the following would be the most effective method to allow the astronaut's center of mass to move closer to the spacecraft? So the astronaut wants to get closer to the spacecraft. You can read the options. All right. Alex Lazada, you have an answer?
Yeah, I got D because like isn't it like Newton's law that if it's an equal and opposite reaction, right? When you push against something.
Good. So every force has an equal and opposite force. If I'm throwing the rock in that direction, the rock is being pushed that way, I get pushed the opposite way. So if I push it away, I get pushed towards the spacecraft. I'm assuming the rock is less massive than I am, so I'm going to move more slowly. You could also do it as like a conservation of momentum piece. I make the rock go that way, so I have to go the opposite way. Okay. I agree. D is the best answer. A and B, I think, are out because if you're moving your arms, every time you move them back, you're doing the opposite part, right? So I could keep doing this, but I'm not net going anywhere. I might move my center of mass forwards and backwards a little bit, but I guess you can't, it doesn't make sense because you can't see my arms. But my overall motion is null, right? All right, cool. Ooh, a block is released from rest. on the frictionless ramp and loop-de-loop. When the block reaches point P, it is moving upwards, and the magnitude of the normal force from the surface is equal to the block's weight. So I'm actually going to draw that in. Normal force would be that way, right? Because it's perpendicular to the surface. F sub n is equal to the weight. Weight is always downwards, F sub g. So in which direction is the block's acceleration at this time? The other thing is I know that it's moving upwards, so that would be velocity. Which one shows acceleration? Unmute and shout it out, or put it in the chat if you got it.
I think it would be B, because in circular motion, doesn't acceleration go towards the middle of the circle?
It does, as long as there are no other forces. You're right, circular motion, the centripetal motion would be towards the center, and that one is represented by the normal force. But we have another thing that's pushing in on this. So like basically if I was flat on the ground, if my circle was flat on the ground, this drawing two-dimensionally is hard for me. But imagine, imagine it's a racetrack circle, not a loop-de-loop circle. Then you would be correct. Then it would always be towards the center of the circle. In this case, you have an additional force, the force of gravity. So your centripetal force is to the center. Force of gravity is down. Where does that lead your overall net force to be?
It'd be C, since it's like in the middle of the two of them.
It would be. It would be C, because that would be your vector addition, middle of the two of them. I know that force is proportional to acceleration. And if we think about it logically, would I slow down as I went up the hill? I would. I would be slowing down, so my acceleration would be downwards a little bit, but it'd also be towards the center based off of Holden's centripetal force piece. So that means down and towards the center, which pushes me there, C. All right. 17. Two rocks are thrown vertically upwards. Rock A, mass equals 3 kilograms, is thrown upwards at 5 meters per second. Rock B, mass equals 6 kilograms, is thrown upwards at 10 meters per second. Which of the following describes the time taken to reach their respective maximum heights and the magnitude of the net force acting on them at their maximum height? So we're looking at time to reach height and net force at the maximum height. The rocks thrown up in the air. Let me know when you've got an answer or half of an answer. If you can answer just the net force or just the maximum height. I would argue they are two different and kind of unrelated answers that we're squishing together into one question.
Would it be D?
Okay. So start with the maximum height. Why? You're saying greater for rock B. Why do you think rock B would go to a greater maximum height?
Because rock B has greater velocity, like initial velocity. So it has it can and the acceleration is constant. So how do I explain this?
Yeah, you're right.
Yeah.
Uh-huh.
Like so it can take more of the acceleration kind of.
Good. It is definitely maximum height is greater for rock B because it's going up twice as fast. Acceleration is down and it's constant. So rock B will take twice as long to reach its maximum height, right? Okay. Then magnitude of the net force. What is the net force of a rock when it's been thrown up in the air and then it's sitting at its maximum? When it's sitting at its maximum height, is it moving? Threw it up in the air. Eee. Boom. What's the force on the rock if I'm not touching it anymore?
It would still be it would still have acceleration, right? Because acceleration is constant.
Good. What would the acceleration be due to?
Gravity.
Gravity. Okay. And which one would have greater force of gravity?
B, since it's heavier, and force gravity is mass times the acceleration due to gravity.
Good job. F sub g is equal to mass times acceleration due to gravity. I know that the acceleration due to gravity is the same for both of them, but the mass is twice as big for rock B. So I agree. That is the correct answer, answer D. Full disclosure, I started by questioning your answer because my first answer was that the net force should be the same for both rocks, because I was just thinking about the acceleration due to gravity. I wasn't thinking about the force. Once again, you've caught me not reading carefully. Good job. And on that note, a nice and helpful thing, like A, you guys are crushing it, good job. B, as it turns out, I went through and did some close research. To get a 3 on the AP physics test, you got to get about 40% of the questions correct. So if you get to one and you're like, God, this just is not making sense to me, give it your best guess. There's no penalty for wrong guesses. So make your best guess and move on. It's okay. There are 50 questions in the first set, 70 or 25 in the second set, and you got to get 40% of them right. So you're allowed to have 1 or 2 misses, probably more than 1 or 2 misses. Cool. 18. We'll see if we can bang through to number 20, and then probably call it good, depending, maybe 21. Cart with ideal linear spring attached collides with a wall. The cart has mass m and speed v, and the spring compresses at a maximum distance of delta x. A second cart with mass 4m, speed 2v, but with the same linear spring attached, also collides with the wall. What will the maximum spring compression be for the second cart? Ooh. See if you can solve this one out. All right, anybody got an answer and a justification? This one I definitely have to do on paper. I can't just logic this one.
I calculated the kinetic energy of the second cart to be 16 times greater than the first cart.
Okay.
Which means that that kinetic energy would be turned into spring potential energy 16 times greater, and therefore compressed 16 times more.
Very, very close. You got the first 3 steps perfect.
Okay.
Okay. So
Where did I go wrong?
At the very last step. So you found, so I'm showing it on my screen.
Mm-hmm.
I agree. I think this is an energy conversion problem. And I have 1/2 mv squared equals 1/2 kx squared for kinetic energy into spring potential energy. Then you have 4 times the mass and 2 times the velocity. So that gives you 16 mv squared equals k is a constant, so that one's irrelevant, x squared. But x is squared,
I'm starting this. Okay.
it would be 4x squared to give me 16x squared. So the 4, it would be 4 times the distance would give me a matching 16 times the kinetic energy. That one track?
Yeah, I see what I did.
Your logic was perfect, except for that little tiny squared piece. So I would go A 4 delta x, and then when you square it, the 16 will match the other 16. Nice. Problem 19, same scenario. A car with an attached spring moving at speed v collides elastically with a wall, bouncing backwards with an equal speed v. Which of the following describe the total work done on and net impulse applied to the cart spring system by the wall during this collision? Okay, so my system is this sucker done by the wall. Okay. And I'm looking at before versus after. All right, anybody have a justification for any element of this problem? So I would start with the work. What is work?
Well, work is force times distance, right? And so the wall is exerting a force like on the spring, so it's a non-zero.
Okay. That's a good logical thought process.
And then I want to say net impulse is 0. Am I wrong?
I believe you are.
Cool.
But it's a good logical thought process. I would start with like, what is work is a form of what?
Oh, it's a change of energy.
It's a change of energy. What's the type of energy that the cart has before the collision?
Kinetic.
Kinetic. Okay. So I start with kinetic energy, which is 1/2 mv squared. What type of energy does the cart have after the collision?
Kinetic.
Kinetic. So it goes from 1/2 mv squared to 1/2 mv squared, but in this case, it's negative v, right? Once I square that negative v, the negative cancels out. And so my kinetic energy ends up equaling my kinetic energy. So my energy before equals my energy after. How much work has been done? 0. You are right that force times distance. In this case, you could make a force times distance piece by arguing that the wall moves 0. There is 0 distance moved by the wall as a result of that force. So I would say we have 0 total work done. And then what about impulse? What's the equation for impulse? Ruh-roh. Did we forget this one? Anybody got an equation for impulse? We can represent impulse as J, or we can also, in your thing, represent it as delta P, I think, on the physics everything sheet. And it's equal to force times time. Is there a force exerted by the wall on the cart? Yes. Is it exerted for a certain period of time? Yes. So
It's a non-zero, right?
it is non-zero. Yep. So there is a force, there is a time. I would argue that that is a non-zero impulse, but a 0 work for part B. All right, last one. Oh God. Now it's an Atwood machine with a spring. Y'all gotta be kidding. Okay. Two masses are connected by a light string as shown below. The mass on the table can slide without friction. The spring has force constant K and the system is released from rest with the spring initially at its natural relaxed length of L sub 0. Which of the following is an expression for the maximum length of the spring? This is ugly, ugly. Okay, give it your best shot. After I've set you up for success so well. Bye. Okay, if it helps, I would set this up as an energy problem. Anybody have thoughts on this one? Okay, so here's my thought process. The good news is that this is effectively, I don't have to worry about the Atwood machine part of it. This is a conversion of energy, and it's going from no spring potential energy. Then as it goes through equilibrium, it'll have some kinetic energy. It'll have kinetic energy, and then it'll transfer, and when the spring is fully extended, it just has gravitational potential energy. So the gravitational potential energy would be like M2 going down by a set amount. That would also, and I'll do that in blue, that would also be equivalent to this spring going out a set distance. I'm going to call that the change of the spring length, which is going to be x. Okay, so the change of the spring, I could also call it y, because this is y, so like delta y equals x. So I would start with this one as spring potential energy at the beginning, so U sub s, turning into U sub g, right? I've got initially spring potential, and then into the next one. So spring potential, 1/2, nope, not m, k x squared will turn into mass times acceleration due to gravity times the height, which is x or delta y. Then solving for x, because x would be the distance stretched, right? And I'm trying to figure out the maximum length of the spring. So solving for x, I could divide both sides by x. That'll get rid of that x and that x, those two. Then I've got mg, multiply both sides by 2. That'll get rid of that part. And then divide both sides by k over k, gives me x equals 2mg over k. That's my x part. And then my total distance, my total max out there would be that much, which is L sub 0 plus x. And that x, L sub 0 plus 2mg over k. So that would be my grand total answer. L sub 0 plus 2mg over k is answer B. All right. What a gnarly place to stop. But it's 9:05. We've gone a little bit over. Thank you for hanging in there and sticking with me. So I'd say there's a couple things, right? Number one, these are hard. However, you have the skill set on how to process them. It's just a matter of getting into that rhythm of like, oh yeah, I could process this one in energy. Oh, okay, I got to include this for this. The other good news is 40% gets it done on a 3. Like 55% gets you to a 4. 70% gets you to a 5. On all of our unit tests, we've been going a notch above that. So I've been scoring on 1 notch over that. So I think we're actually in pretty good shape. Yeah. All right. I am gonna stop